thank you, Jackie. So I guess you've been warned, you better pay attention. But it wasn't me that said it. So when Jackie invited me to come give the Smith lecture, my initial response was, wasn't I just there? But I checked my calendar, and it was 6 years ago, the last time I was here. And I assumed that at that time I talked about shockwave experiments, which is what I spent most of my time doing and most of my time thinking about. But today I'm going to do something else altogether. I still keep a foot in shallow upper mantle igneous petrology and mid-ocean ridges, and this is something that's been bothering me now for about 4 years, that I haven't ever really assembled together and written about or gotten up and talked about. But it's what I call the mid-ocean ridge basalt ferric iron crisis. And since I sent you the title of the talk, I've added a question mark because now that I am going around talking about this, people have suggested to me that maybe there isn't a crisis after all. But we'll try to decide that by the end of the hour. So I'm talking about mid-ocean ridge basalts, which are wonderful rocks. You go out to a mid-ocean ridge, you dredge, and you pick up these rocks, and they have glassy rinds, where the pillows have come into contact with seawater and quenched very quickly, and you can just break off the glass. And this is incredibly important in the history of igneous petrology. We go all the way back to Bowen and the evolution of the igneous rocks. Bowen taught us all how to think about differentiation of basalts leading to andesites and dacite and rhyolites. And it was all based on the idea that when you take an igneous rock, which is made of minerals, and you imagine that it was a liquid, that you find systematic relations among those compositions that you can understand in terms of fractional crystallization. But it all depended upon this inference that your rock was actually a liquid composition, which in the case of a crystalline rock is never actually true. In the case of a glassy rock, it is actually true. The way you make glass is you quench a liquid. So mid-ocean ridge basalts have been incredibly influential in our thinking about igneous petrology in general. But specifically, mid-ocean ridge basalts have lots of additional advantages. They are forming in the absence of any continental crust or any pre-existing crust at all. They're coming straight out of the mantle, and therefore they are our best messengers from the interior of the Earth, and they give us our best chance of inferring the composition of the upper mantle, the temperature of the upper mantle, all sorts of fundamental things that we would like to know. These rocks come out of the Earth, they quench to a glass, we can pick them up, we can analyze all kinds of things. But some things are easier to analyze than others. And so, given some glass, you can measure major elements by electron probe or bulk techniques. You can measure the trace elements, the isotopes, uranium series disequilibria. You can measure volatils like water and CO2. You can measure the oxidation state by 3 different techniques that have been proposed: wet chemistry, Mossbauer spectroscopy, and X-ray absorption near-edge spectroscopy. You can do the petrography and see what sort of phenocrysts are there. Within the phenocrysts, you can look for melt inclusions and apply all these techniques to those little bubbles of glass that are trapped inside. And after you've measured all of those things, or some of those things, of course, you have science questions that you wish to address using these rocks. Right? You would like to know the composition of the mantle source. Right? What is the Earth's mantle made of? And can we use igneous rocks that were derived from partial melting of that material to infer what that material was? We'd like to know the temperature of the mantle source and how it varies around the Earth. This is a really fundamental aspect of the way plate tectonics works, and it's a very difficult thing to measure in most places. Mid-ocean ridge basalts give us our best probe, actually, of what is the temperature of the upper mantle, and how does it vary around the world's oceans. There's lots of other things you might want to know. From a petrological perspective, you'd like to know the extent of melting that was involved in going from mantle rock to crustal rock. You'd like to know how much fractionation occurred after that primary magma came out of the mantle and cooled and differentiated and left behind crystals. How much mass fraction did you leave behind before you got the basalt that was eventually going to erupt on the surface? And that relates to the origin of the oceanic lower crust, this thick layer, 3 or 4 kilometers thick of cumulants, of plutonic rocks that makes up the lower crust. You'd like to be able to infer the origin of the lower crust from observations of the upper crust, if you can. And of course, fractionation and cooling of these basaltic lavas as they make the lower crust and eventually erupt to form the upper crust, provide the heat which drives the hydrothermal systems, which are one of the most exciting things about mid-ocean ridges and figure in the geochemistry of the ocean and the seafloor and possibly the origin of life and so on. And knowing how much fractionation is involved, knowing ultimately how hot the primary liquid was when it came into the crust, tells you a lot about that. So what I'm going to focus on in this lecture is the fact that there are many, many thousands now of analyses of the major elements of mid-ocean ridge basalt glasses. It's very easy to do. Electron probes are cheap, widely distributed, everybody's got one, and so you can pick up lots of basalt glasses and you can measure them. On the other hand, the electron probe measures only total iron. It doesn't tell you how much of the iron is ferrous, iron 2+, and how much is ferric, iron 3+. That's a different analysis. And this has only been done a few hundred times. Okay? It's a much more difficult measurement. And the point that I'm going to try to make in this lecture is that what you think the oxidation state of fresh mid-ocean ridge basalt glass is has a strong effect on what you think the temperature of the mantle source was, which in turn has a strong effect on the extent of melting, the extent of fractionation, the origin of the lower crust, and the amount of heat available for the hydrothermal systems. This turns out to be a key measurement, which is widely assumed to apply, based on a few measurements, to essentially all mid-ocean ridges. And those few measurements don't agree with each other, which is the origin of the crisis. Okay, so let's just remind ourselves about iron. Iron exists in nature in 3 oxidation states: metallic iron, iron 2+, or ferrous iron, which in rocks we express with the component FeO, and iron 3+, or ferric iron, which we express in rocks with the component Fe2O3. Okay. As minerals, these are iron, rustite, and hematite. Rustite you very rarely see in pure form, but there's a picture of what it actually looks like. And there is, of course, a relationship between the speciation of iron in a magma and the oxidation state. Okay. And you can describe the oxidation state either directly by saying this is how much of the iron is ferric, or you can use oxygen fugacity as a proxy for expressing the oxidation state. Oxygen fugacity is a sort of a difficult concept to wrap your head around. Okay. In air, the oxygen fugacity is 20% of 1 bar. That's easy. In rocks where there isn't any gas around, you can be many, many, many orders of magnitude lower than air in terms of your oxygen fugacity. It just provides us a reference number that lets us describe how oxidizing or how reducing things are. We're going to be talking in this lecture about this range here, from about 2 log units more reducing than the quartz sphaelite magnetite buffer to about half a log unit more oxidizing than the quartz sphaelite magnetite buffer. Okay. Which means we're going to be talking about ferric iron over total iron contents from about 7% to about 17%, or conversely, ferrous iron over total iron from about 93% down to about 80%. This is the range that has been proposed for mid-ocean ridge basalts. It's a small range in the overall scheme of things from the core to the atmosphere, but it's enough of a range that I will hopefully show you that it really matters where on that spectrum we are. So the first point is this is a really difficult measurement. To measure the iron 2+ over total iron of a mid-ocean ridge basalt glass. There are issues with all of the available techniques. And let me go through a few of the analytical issues without belaboring them at too great a length. First, you have to decide whether you're going to measure the whole rock, the pillow that came out on the seafloor, or just the glassy rind. And those may not give you the same answer because during cooling and interaction with seawater, you may well be affecting the oxidation state. Okay. If you decide you do want to focus on the glass rind, which is probably the best way to get back to the redox condition that applied in the interior of the Earth, okay, you have to figure out at what scale do you actually know that your glass is glass. If you need, let's say, a gram of material chipped off the outside of a pillow, it's probably going to have some plagioclase or olivine microphenocrysts in it, possibly too small for you to see optically. Okay. And so any bulk technique that involves dissolving a whole bunch of glass may be contaminated by other phases. Whereas if you go to the electron probe and you go down to 1 to 10 micron scale and go to a backscattered electron image at the same time that you're analyzing, you can be sure you're truly analyzing glass. But as we will see, a lot of the measurements that we're dealing with involve combining one analytical technique for total iron and a different analytical technique for ferrous iron, measured at different scales on different aliquots of the sample, which is a potential source of error. Okay. The next problem is that there is no good way to measure ferric iron directly. Okay. And so what people do is measure total iron and iron 2+ or FeO, and they take the difference. And this is the difference between two large and nearly equal numbers, because there's only something like 5 to 15% ferric iron. And so the errors on both of these numbers really matter. You've got to beat them down carefully, or the combination of the errors blows up. The techniques that are involved in measuring ferrous iron, okay, are mostly relative techniques, not absolute. They have to be calibrated. And the calibration is ultimately traceable to Mossbauer spectroscopy, usually, which is an absolute method, but it's an absolute method that requires a lot of sample, and so it can be contaminated by these issues of homogeneity of the glass. Okay. For the last 50 years or so, the typical technique has been to measure total iron by either electron probe or a plasma-based spectroscopy technique or X-ray fluorescence, and then to measure iron 2+ by a wet chemical technique where you get the glass into solution and you either measure the absorption of certain wavelengths of light, which are characteristic of iron 2+, this is what Becky Lang does, or you do a chemical titration where you dump various chemicals into the solution and see how they react and titrate to the endpoint. Just for the fun of it, this is the page from Dean Presnell's thesis from 1966 that gives the method for how you actually do this method in wet chemistry of measuring both total iron and ferrous iron. And it's so scary, the number of things you have to do and the number of places you can make an error. It's really quite remarkable that people got anywhere before things like the electron probe came along. And yet the electron probe doesn't solve our problem. We still need to do something like these very difficult wet chemistry methods in order to get at the ferrous iron content. So, as a result of these analytical difficulties and disagreements about what you should measure, the number has been changing over time. Okay, so before 1986, everybody's favorite number was about 85% ferrous, or 15% ferric iron, and this was based on wet chemical analyses of whole rocks, of pillow materials. Okay. Christie et al., in this classic, very influential paper in 1986, got enough glass from enough places on the mid-ocean ridge to do this analysis on the glass rind, and they did both electron probe and directly coupled plasma measurements of total iron, and they did wet chemistry by the Carmichael colorimetric technique for Fe2+, and they got much more reducing conditions. Okay, they got ferrous iron over total of 0.93. I'll give you a little table down here that will help you think of the three different ways that I'm going to express this quantity. Okay, so Christie's number is 93% ferrous iron or 7% ferric iron, which turns out to be an oxidation state about 1.2 log units below kilotherm. And that was the number for about 20 years. And then Bezos and Humbler used a new titration technique, okay, to redo this analysis, and they came up with iron 2+ over total iron of 0.88, or ferric iron over total iron of 0.12, which is much more oxidizing conditions, about 0.8 log units higher. And that was okay. That did not yet create a crisis in my mind. But then Liz Cottrell and Katie Kelly came along in 2009 and 2011, with a new measurement based on the very high-tech GWIS method of X-ray absorption near-edge spectroscopy with a synchrotron beam where you get down to very small scales. And they determined that actually the ferrous iron content over ferric iron is only 0.84, or about 16% ferric iron, or an FO2 that's actually higher than kilotherm. Okay. And this is the number that made me think, is that for reasons I will show you, that there really is a crisis. Okay. If this is the number, then I have a lot of problems that I'm going to share with you in the next few minutes. Okay. But the reason one reason there may not be a crisis is that at Goldschmidt this summer, when I gave this talk, a version of this talk, everybody came up to me and said, no, the number's not actually 84. The Minnesota